say 2.5. So now plus sign, that is where servo amplifier gain. We use whenever if you use this K is called as your gain value, gain of your amplifier. Then this were inner loop plus minus. Then we combine both these transfer function, aircraft as well as elevator transfer function, that is called as your 12 times of S plus 0.585 then S plus 10 into S square plus 1.5S plus 1.47. Then from that we get rate, velocity rate feedback, pitch rate feedback. That gyro sensitivity, rate gyro sensitivity value, we found the value say 2.5. For having a higher damping, we choose the damping is 0.877. This for theta dot. If we integrate this, we will get theta. That I push in 1 by S. Then we will get theta. That will be feedback to here. Kinetic feedback. This is called as well theta. This will theta reference. Okay. Now we these were inner loop. Now we reduce this inner loop. This were inner loop. Okay. You see here inner loop, that is called as your negative feedback control system. It's because the theta dot is a feedback with the minus sign here is a negative feedback control system. So if we consider this, if these whole things if we consider say G of S, then it is a negative feedback plus minus sign, where H of S to be your feedback here. If it is this is a H of S, then the whole transfer function, if you want to reduce this block, then it is called as well G of S, a transfer function, TF, a transfer function, G of S divided by 1 plus G of S into H of S, because it is a negative feedback control system. That's why here we use a plus sign. Therefore this transfer function for this inner loop, this is your inner loop. Okay, that is what is your G of S. G of S here 12 times of S plus 0.585, S plus 10 into S square plus 1.5S plus 1.47, where H of S to be 2.5. Therefore we apply this equation, 12 S plus 0.585 divided by S plus 10 into S square plus 1.5S plus 1.47. This were G of S divided by 1 plus G of S, again 12 into S plus 0.585 divided by S plus 10 into S square plus 1.5S plus 1.47 into where H of S value, this feedback is 2.5, we multiply with 2.5. Therefore your transfer function, if you cross multiple, then we common divide S plus 10 to S square 1.5S plus 1.47, both will be cancelled. Therefore we will get 12 into s plus 0.585 divide by, if we cross multiple this value, then 1 into s plus 10 the whole thing, then we will get s plus 10 into s square plus 1.5s plus 1.47 plus 12 into s plus 0, 12 into 2.5, 12 into 2.5 we will get 30. So we use here 12 into 2.5, just multiple these two values, means 12 into 2.5, that will be get 30 times of s plus 5, s plus 0.58. Okay, that is, then divide by s plus 10 into s square plus 1.4s plus 1.47. This term will be cancelled. Once we cross multiple, then we cancel this term. Therefore, your transfer function for your inner loop, what is your the closed loop transfer function of your inner loop? We remove this entire loop, then we put as your transfer function 12 times s plus 0.585, then divide by s plus 10 into s square plus 1.5s plus 1.47. Again we simplify this. So what is your transfer function for your inner loop? Transfer function is to be 12 times of s plus 0.585 divide by, if you multiple s plus 10 into this s square plus 1.5s plus 1.47, s into s square will get s cube, then plus 1.5 s square, then plus 1.47s, then if you multiple 10 we will get 10 s square plus 15s, 10 s square plus 15s, then 1.47 into 10 we will get 14.7 plus 14.7, then we multiple inside 30s plus 30s, and plus 30 into 0.585 multiple with 30 into 0.585, we will get 17.55 plus 17.55. Therefore, your transfer function for this inner loop 12 times s plus 0.585 divide by s cube plus 1.5 s square plus here 110 s square, then we will get 16.5 s square, then here 30s plus for 15s 45s plus 1.47, then we will get 46.47 yes. Then here 17.55 plus 14.7, we get 32.25 plus 32.25. Therefore, we remove this inner loop. Then we set your transfer function TF is equal to 12 times S plus 0.585 divided by S cube plus 16.5 S square plus 46.47 S plus 32.25. Now we remove this inner loop. This is inner loop. We remove this inner loop. What is the transfer function of their inner loop? Twelve S plus 0.585 is whole thing divided by what is the inner loop transfer function? S cube plus 16.5 S square then 46.47 S and 46.47 S then plus 32.25. Now it is your outer loop of your jet transport aircraft, yeah, autopilot system. Okay, so here these two block is again multiple, then 1 by S into this whole thing, then again we will get 12 into S plus 0.585. If you multiple with 1 point S this block, then this S cube term now it will comes to S power 4, then S square term come to S cube, then we multiple with 1 by S, then it will get S power 4, then it is 6.5 S cube, then it is 46.47 S square, then it will get 32.25 S. Now we remove this 1 by S also. Now this is your outer loop. So now we are going to sketch the root locus. Initially we assume a amplifier gain is to be 1 for your outer loop of your autopilot system of your jet transport aircraft. Okay, now they use your what is your transfer function. So we simply use this command in MATLAB. Your numerator having transfer function is 1, S coefficient is 1, then 0.585 and 1 0.585, then your denominator having transfer function, the coefficient S power coefficient is 1, then x cube is 16.5, then 46.47 S square, then 32.5 S. There is no constant term, therefore the coefficient is 0. Now my transfer function, if you consider these whole things G, then your G is equal to 12 is there, therefore 12 times of your transfer function, 12 times of my transfer function TF, I define numerator comma denominator. Now I sketch R locus of my G. I use this command, then we sketch the root locus for your outer loop control system. Go to MATLAB, choose this one. Use this. You see here, your numerator having the coefficient is 1, 0.585. My denominator having the coefficient is s power 4 coefficient is 1. Then s cube is, we get 10.5. 1 minute, we get 16.5. 10 into s square, and 1 we will get 1.5 s square. Then we will get s cube plus 16.5 s square. One minute. 46.47, then 32.25 is there. We will get 10.5. What we get here? Multiple s square into s, we will get s cube, and 10, 1.5 s square, and plus 10 s square. We will get 10 s square, then we will get 1.5 s square, and here 1.5 s square, here 10 s square is there, so we will get 11.5 s square. So here, if we multiple, we will get s cube 1.5 s square plus 1.47 s, and 10 s square plus 1.5 s square, and we will get 11.5 s square, not 60. 11 point s square. 5 s square plus 46.47 s plus 32. Okay. This will be 11.5. 46.47, then 32.25, that coefficient is constant coefficient 0. Then your transfer function g is equal to 12 times of your transfer function numerator comma denominator, then we check your root locus. This is a root locus study for your outer loop system. These were root locus branches for the outer loop system. You see here, this outer loop holds when the gain is 0, that it is having a damping is 0.871. Come along this direction. Yes, we put initially, if you see here, in the previous case, I select my gain value is 2.5. That means the rate guided sensitivity gain is 2.5. My damping is 0.871. 0.871. You see here, my damping is 0.871. Okay, so if you initially the gain is 0, that is 0.871. If you increase my gain value, this tendency to reduce, it will increase like that, it will comes to here. If you look at my gain value is 3.6 or 3.88, go along this direction. If I increase my gain value, suppose my gain is 3.88, that will go leads. Then if you increase your gain value, your damping will be reduces. Okay, these gain values almost 3 point or 4, if we select 4.7 or 3.8. You see, if we go along this direction, my damping is reduced. So while if you having higher damping as your inner loop, that is tendency to pull this closed loop system to lesser damping. Okay, so if we see, if we increase my rate gyro, so the amplifier gain value, my damping will be reduces. See here, my damping goes 0.226 if I have a gain value is 13.9. Therefore, slightly we need to have a higher damping value, because if you have a higher damping, then we have lesser overshoot. Therefore, we keep the damping is for all this almost 0.7 or higher than this 0.6. Select 0.72 or 7, 0.769, 0.425, it will become 4.15. This will call this where if the gain is 4.15, my damping is 0.8. Okay, so if we keep on increase your gain value, it is a tendency to this closed loop moves your right hand side of the spec. So where your gain values, if you see here, if you go your gain values is 35.8. If you put your amplifier gain is more than 30.58, the system comes to unstable. See, where when the root locus branches cross the imaginary axis, my maximum gain value of amplifier is to be 35.9. If this 35.9 I have lesser damping. That means that almost the damping is zero. Almost the damping is zero means the system having 100% overshoot. If it is 100% overshoot, then the system having oscillatory response. Therefore, the system is marginally stable. The system is to be marginally stable. Okay. So that's why we select your rate gyro sensitive feedback values for a higher damping. If we select higher damping, so if we select the rate gyro sensitive value is this case, my rate gyro sensitive value is 2.5, my damping ratio is 0.871. So if the inner loop is having higher damping, that outer loop, all because the outer loop is outer loop poles, the outer loop of your closed loop poles are tendency to reduce your damping. That's why we are selecting the inner loop having a higher damping. So if we select your damping ratio is 0.871, that rate gyro sensitive value is 2.5. Okay, from that we observation we came to know that there is a essential for rate gyro sensitive. If we select your, if you put the rate gyro sensitive feedback, then I have a higher damping. If you have a higher damping, that will be leads to reduce your overshoot. So I will give to assignment to you. We try to sketch the step response of your inner loop with rate